Okay. Okay. Good morning, everyone. So last time we have been talking about how to apply the quantums into the consideration of the solely, especially in the case for our semiconductor, and we talk about some basics statistics that how we are able to analyze the carriers by using the certain statistic function. So from the previous several weeks lecture, I believe that we have enough fundamental knowledge. Now we will move on to the case that our goal is to try to analyze the concentration. So therefore, in today's lecture, we will focus on how to analyze the carrier concentration. And then for sure that in the beginning, we will focus on the most simple case where is a semiconductor in equilibrium, which means that this is a case that doesn't have any additional bias or light. So it's everything is under there's no external force. So this is a case we call the semiconductor in equilibrium. So first of all, just a brief mention that what you'll be able to learn by end of these lectures. Here you are able to explain the carrier statistic in semiconductor. So in last week we have mentioned the basic statistic, but now we will apply to the case in the semiconductor. So you'll be able to describe the equilibrium distribution for the electron holes in the conduction band and valence band. So that's very crucial because that's fundamentals to help us to estimate the carrier concentration, and also we are able to apply the certain approximation, but anyway the goal is to try to estimate the carrier concentration. And also the second, we are able to, by this end of this lecture, you are able to analyze the intrinsic semiconductor property. For example, you are able to analyze the intrinsic carrier concentration and also the intrinsic Fermi level. So these are very crucial to understand the basic characteristic for the one kind of a semiconductor. We're always starting from the intrinsic case. So we'll talk about intrinsic carrier concentration, we'll talk about the intrinsic Fermi level. And also, by understanding the intrinsic carrier concentration, and we are able to interpret that how the temperature and band gap will affect the intrinsic carrier concentration. So that's also the very important implication that we can learn from the intrinsic carrier concentration. And also, furthermore, we will start to discuss the doping on the semiconductor, distinguish between the N-type and P-type semiconductor, and also it's very crucial to understand donor and acceptor energy level, and also the ionization mechanism here. And finally, we are able to calculate the equilibrium carrier concentration. So we'll apply the certain very basic foundation. For example, we apply the charge neutralities, we apply the mass action loads in the end to determine the N0 and P0 here. And 0 here means that this is a case under the equilibrium consideration. And also, we are able to understand the position of Fermi level with respect to the different doping concentration. So that's a very crucial. In the beginning, we will try to derive, but in the end, you should be able to absorb this knowledge in your mind that become a kind of intuitive in the future once you try to address the issue that for your practical case, nobody will do this fundamental calculation. We just intuitively apply the intrinsic Fermi level and also the Fermi level to understand this is in the case of the N-type or P-type semiconductor. But still, in this class, we will go through these foundations again. So finally, there's a very crucial concept. It's a little bit difficult. We won't talk about this in detail, but there's a small part of the inside this chapter. You look at textbook, we'll talk about the difference between the intrinsic, extrinsic, and degenerate semiconductor. For real case, it's very often to look at what does mean the intrinsic, extrinsic, and degeneration. But in here, for sure that we are still in the basic that we will quickly go through the equation. But in the future, I believe that once you face the real issues that you need to address, you should be able to look at again the fundamental, the definition between the intrinsic, extrinsic, and degenerate semiconductor. Okay, so first we're back to the what we have been known so far, and we start from the state by state to goal toward the goal is to analyze the charge carriers in the semiconductor. So from the previous lectures, we have been known that there is a very well-known distribution that we call the Fermi-Dirac distribution. Fermi-Dirac distribution, and that's we have been learned from previous lecture. And then by definition, this is a distribution written where we have the NE over GE equilibrium to as a Fermi energy, and then the NE here it means number of the carrier. And then the GE is a number of the quantum state. That's something that we have been mentioned last time. So we were starting from here. And therefore, with considering this Fermi-Dirac distribution, our goal is to estimate the number of a carrier. So therefore, we can start to do a very simple mathematics here. So we are able to estimate the number of the carrier is equal to our GC times our FE here, right? So this is a equation that coming from the right hand side equation, and with considering as a thermal equilibrium case, therefore we can rewrite the NE become as a N0, where the 0 means this is a thermal equilibrium case. So the thermal equilibrium case is equal to the integration of a GCE times FFE over the energy integrated of the energy level. So that's a thermal equilibrium electron concentration can be shown in here. So where is integration of this number of quantum state times our Fermi energy here, and then we are able to analyze the thermal equilibrium carrier concentration. So now, with considering for electron in the conduction band, we have energies larger than EC, and also if in the case of EC minus EF, which is much larger than the KT, then this will also be much larger than KT. So in this case, we are able to apply the Boltzmann approximation where we have already shown in the last time. So this Fermi-Dirac distribution will be approximately equal to this one, exponential minus E minus EF over KT. So that's our Boltzmann approximation. So now we just try to put everything we know so far. So where this one is here, right? So this is something we showed in last week, which is in here. And therefore, finally, we can have this general description as shown here as an equation. We are able to analyze the thermal equilibrium, electron concentration, where this term and this term, which are G, C, and also the F, F, E, respectively. So this is something that we learned from the previous lecture. We just right now try to combine everything together, and so far the mathematics is not very complicated, just putting everything together. Okay, so let's start to move on. So finally, we are able to have this equation that we still back to this general form where our N0 is equal to the integration of this GC and times this distribution. Therefore, of course, this equation looks a little bit scary in the last slide, but we can have a more simple way to try to plot this equation that would be more easy for us to understand. So in this case, we prefer to explain in the way that we considering the case with the band gap here. So therefore we will have the inside the band. So we have the conduction band, the top of the conduction band, and also the bottom of a conduction band and the top of valence band, which is denoted as EC and EV here. And then also from last week, we have been already, from the previous lecture, we have been already knew that this GC has this kind of curve, which will be look like in this way. So this is our GCE here. And also our FFE is with respect to the different Fermi energy. If we assume our Fermi energy is here, so that's our Fermi energy, EF here. And as we shown last time, that with respect to the Fermi energy, then we should be able to plot the Fermi distribution, which will be similarly like with this case. And where this point is FFE here. And similarly, we can also start to consider the GV, where is below the valence band, which we have this one. So now, try to think about this equation again. This equation actually tells us that the integration between this one and this one, which in the end will be the area of these two curves overlap. So therefore we can simply to get the conclusion, which is GCE times FFE here is equal to NE, and which is this area. If you try to plot in here, so this area, which is N0, the thermal equilibrium electron concentration. Right? So we don't really have to calculate the very difficult equation. By using this plot, we can simply estimate the overlap area, which is thermal equilibrium electron concentration. Similarly, this overlap region in here which is GVE times the 1 minus FFE, which will be equal to the whole concentration, which is the area as shown here is equal to the thermal equilibrium whole concentration So now we are able to understand what does this equation tell us. So this equation tells us that the integration of this GC times our distribution, we are able to estimate the area, which is the electron concentration. We are able to estimate the area where is the whole concentration as shown here. So let's just try to do once what is exactly this equation will be look like. So if you really put everything inside, so we can able to have this one come out, and also we can define this term, which is NC here. So we call this as a effective density state function in the conduction band. So we define this as a constant called NC. So therefore, the N0 can be rewritten as shown me here, which is equal to NC exponential minus EC minus EF over KT. So this is a very well-known equation that you definitely need this equation to estimate the carrier concentration. And we need to further try to understand more about this equation, not just as an equation itself. It's an implication, it's a physics implication coming from this equation. This equation actually also tells us that if you look at the band diagram, where we have the EC and EV, but now if we consider the case where our Fermi energy is no longer in the middle, So let's assume the case our EF is close to the EC. So in this case, it's very simple. Once our EF close to EC, for sure, EC minus EF is getting smaller, right? So if EC minus EF is getting smaller, that means exponential this term EC minus EF over KT, this term is getting larger because this is exponential minus. So if minus ECEF minus EF is getting smaller, the exponential minus of this term is getting larger. So that means we consider this case. This is a case where our electron concentration is increased. So then this will become a semiconductor material that N0 is larger than P0. So if you have a piece of a semiconductor that N0, your electron concentration is larger than the whole concentration, what does that mean? That means this is become as a N-type semiconductor. So for me, the most important meaning of this equation is beyond the purely calculation. For sure that you will definitely practice several times by using this very simple equation to estimate the thermal equilibrium electron concentration. But for the reality, we won't calculate the carriers by ourselves. For most of the cases that you will face in the future, we never try to estimate the carrier concentration by ourselves. But we do need this concept. We need this concept that using the Fermi energy close to the conduction band or far away as a conduction band to determine this is a N-type of a P-type semiconductor. I believe this concept is way more important than this equation calculation, because in reality, we only see this graph, and then we need to immediately figure out this is an N-type semiconductor. If we have the EF close to the EV, we need to immediately figure out this is a P-type semiconductor. So this important concept is mainly coming from these equations. So as the same, we can do the same things for the whole concentration. So show me here. So we just try to put every things we have that we have already shown that the PE is equal to this term, and then with a certain calculation, finally we are able to see, we are able to get this P0 is a term with a equation, but in the end it's highly correlate with EF minus E. So that means that with a different energy level, you should be able to get the different carrier concentration. And as we have already mentioned that during this calculation, we try to put a lots of the constant term as a one general term. We call the NC and NV, because these two constant value is only depends on the material's properties, not related to energy level. So therefore we try to make this as a constant. That will be more easy for the future calculation. So you will find out that the NC and V with respect to the different materials as shown me here. And once we start to have the way to estimate the N0, we have the way to estimate the P0. The next concept we have to learn is that what does mean the intrinsic carrier concentration. So the intrinsic carrier concentration is considering that as a special case that we call as an intrinsic semiconductor. Of course, the term sometimes is not very straightforward because in the typical, if you try to translate in the Mandarin, we never say something intrinsic. It's a very vague word. But in general, the intrinsic is just in the case where our electrons concentration equal to the whole concentration. So if we have a material that has an electron concentration is equal to the whole concentration, and this is a material that we call the intrinsic semiconductor. And the Fermi energy level of this intrinsic semiconductor is we call the intrinsic Fermi energy. So, in this case, our Fermi energy, EF, can be rewritten as a EFI, because this is a case of the intrinsic case, so that's what we call as a EFI. So now we can try to replace all the EF where we have learned in the previous slide and replace the EF as a EFN. Now we have the carrier concentration becomes the intrinsic carrier concentration as long as our NC exponential minus EC minus. Now we replace all the EF as a EFI. So now the N0 will become the NI. KT. So that's our intrinsic carrier concentration, where we just put it here as an intrinsic Fermi energy. And similarly, we can do the one things. We can, using the same concept, apply to the whole concentration. In the case of the intrinsic whole concentration, Pi, which is equal to as we previous already shown, this is NV exponential minus EFI minus EV over KT. So we just put we just replace the EF as a EFI as shown here. But the one more thing is just reminding, this is a case as we call the intrinsic, where our electron concentration is equal to the whole concentration. So that means this is a condition that the whole concentration should be exactly equal to electron concentration, Ni here, right? So far, everything calculation is very simple. Just replace several concepts. Just put the additional concept and then put in there and replace them as a EFI and Ni or Pi. That's all. So in the end, so we are able to estimate this equation where we will have Ni squared is equal to NC NV exponential minus EC minus EV over KT. Because you try to put this together then you will get this equation. And also, the EC minus EV here is exactly equal to the band gap, right? So as we already shown, the EC-EV and the difference between the EC-EV is a band gap. So therefore, we can still rewritten as this equation become NC NV exponential minus EG over KT here. So now we finally get a conclusion that the intrinsic carrier concentration is certain correlated with our band gap and also the temperature. So the intrinsic carrier concentration is a very strong function of a temperature and band gap. This is also a very important conclusion, because later, by considering this conclusion, we are able to reconsider several different materials that give us an additional advantage just based on the concept related to the carrier concentration, Ni, related to the band gap, related to the temperature. And also one thing I want to remind that the Ni, intrinsic carrier concentration, is a very important value, and normally for silicon is at a value of 1.5 times 10 to 10 in this kind of order, and then normally it's very important that typically we almost will memorize this value, because this is a value that you are able to compare with the other material to understand whether other material has a lower or higher intrinsic carrier concentration. Of course, for the exam, for the homework exam, you will definitely need to calculate, estimate this Ni intrinsic with respect to the band gap. But for the courses, for the physics-based understanding, we need to further interpret this equation that more realistic to related to our real cases. So let's just try to understand more about the concept of this intrinsic carrier concentration. So as previous already mentioned, that the intrinsic carrier concentration is a very strong function of the temperature. So now in the previous equation, now we can rewrite it that the Ni is equal to and this will be equal to this one. Eg minus 2kT here. So now we can understand that our Ni is certain correlate with temperature here. So therefore, it's very often to try to look at the temperature dependency of the carrier concentration. So assuming it's here, this is a typical plot for the carrier intrinsic carrier density versus the temperature dependency here. But just a reminder that normally we will plot the x-axis as a 1 over t. This is a reason because this here is a 1 over t here. So sometimes we will prefer to plot the Ni versus 1 over t rather than just as a t. It's plotting as a 1 over t. So if you look at the 1 over t in the x-axis, that suggests that toward the left it's a high temperature. And toward the right is a low temperature. So now you can see that this is a silicon. Let's just assume we are focused on the silicon only at this moment. With increased temperature, actually your intrinsic carrier concentration is increased. And with decreasing the temperature, your intrinsic carrier concentration is decreased. So the intrinsic carrier concentration is determined by the thermal generation of electron hole pairs across the energy band gap of the semiconductor. So means if you look at the band gap here, where we have the conduction band, we have a valence band here. And we have been knowing that below the valence band, there are lots of electrons here. But with the temperature increasing, these electrons will be able to acquire the thermal energy and jump over this forbidden band gap and reach to the conduction band. And so that's it's a factor determine the intrinsic carrier concentration. So now if you have this concept and look back to look at this plot, probably you will get a more physical sense that why we go to the high temperature, our intrinsic carrier concentration is increased. This is because the higher temperature we are getting more and more electrons. We're getting more carriers. Let's say that we're getting more carriers. We have more carriers across the band gap. Right? So that's a same as indicate here. That's why the high temperature we get a higher Ni. So therefore, I hope that beyond this equation, you will get more physics-based understanding, not just memorize this equation. For equation, for sure, you can easily to get a conclusion the temperature increase, Ni is increased. But for physics-based understanding, there's also the one way that consider like you have a carrier will be able to jump over your band gap due to the thermal energy. Of course, you go to the higher temperature, you get more thermal energy. Then your carrier is getting more easy to cross this band gap. So that's why you get a higher Ni. So that's a physics-based understanding, which is more important than this equation. But this also reminds us that because you have more carriers that be able to jump over the band gap and reach to the other side. So that's become as a kind of a leakage current. So normally, high temperature, you will very often see your semiconductor device has a higher leakage current. If you already have the experience to measure, to characterize your semiconductor device, for sure that the high temperature, high leakage current, that's almost like universally happen in all of the semiconductor device, unless there's a very unique mechanism. But for most of the cases, it's always high temperature, high current. And the fundamental reason is coming from here, because of you have more carriers jump over your band gap and reach to the other side, and that's why you have a higher current here. And with considering these concepts, that leads to us one additional consideration that where we are able to make the Ni as smaller as possible. If you look at this equation, so far we only talk about the temperature dependency. So we look at the higher temperature, this Ni is increased, that causes a higher leak current. But on the other hand, if we can find a material that has a large band gap, if Eg is become larger, that means our Ni can be decreased. Then ideally, that should help us to reduce the leakage current. So that's why in the next slide, we'll talk about the intrinsic carrier concentration versus the band gap. So the idea is also simple. Many come from this very simple equation where we have been shown our Ni is equal to Nc Nv exponential minus Eg over 2kT. So from this equation, you should find that this Ni is not only dependent on the temperature, but also dependent on the band gap. And this equation also tells us that if we have a material that has a larger band gap, then we should have the material that has a lower intrinsic carrier concentration. And this back to our materials science, back to our materials fundamentals that several weeks ago we already talked about the concept of band gap. And we have been mentioned that silicon for sure is the most important material. This is silicon, and we have EC, EV, and then the band gap for silicon is 1.1 electron volt. But beyond silicon, we still have so many fantastic semiconductor material, and then silicon carbide is one of them. Very promising. Gallium nitride is also one of them. Very promising. One of the reasons why silicon carbide or gallium nitride are very attractive is because of they have the band gap larger than 3 electron volt. Gallium nitride has a band gap larger than 3 electron volt. So this is a semiconductor we call as a wide band gap. Of course, if you look at silicon carbide, gallium nitride, there are lots of materials properties that have shown the advantage compared to the silicon. But right now we don't consider that. We just consider band gap. Just purely consideration of band gap, that's already can show some interesting advantage. So normally if you don't really do the materials analysis, you just didn't know how to measure the intrinsic carrier concentration, is fine. From this fundamental equation, that already tells us that the wide-bandgap material should have a lower intrinsic carrier concentration. But in reality, it's true if you look at this experimental data from here. This is experimental measurement result for the intrinsic carrier concentration versus temperature. So now you can see this is a silicon with increasing the temperature. Actually, the Ni is increasing, which is consistent that we have been described in the last slide. And this is because the silicon only have the band gap 1.1 electron volt. But now if you look at this material that have a band gap more than 3 electron volt here, then you should be start. Forget the equation. Look at this experimental result. You can already see there's a dramatically decrease of the intrinsic carrier concentration is lower Ni. Right? So this decrease is up to more than 5 orders smaller than the silicon. So now you back to the what we get the conclusion from last week that the intrinsic carrier concentration is related to the thermal generating carrier that across the barrier in the end leading to the high current. But now if we have a lower intrinsic carrier concentration, that means we can expect this material that can provide the advantage of a low leakage current. Of course, silicon carbide GaN nitride has a different kind of carrier transport device architecture, but so far we don't have to think about that. We just think about the very fundamental, purely from the band gap. What the band gap can tell us, we can already expect that the silicon carbide GaN nitride can have the semiconductor that have a lower leakage current. So with considering the lower bulk leak current at a high temperature, so what does this suggest for the application? What's the application we need? That we need to have a lower current at a high temperature. That's at the case of the high temperature application. Because in the case with a high temperature application, we need to make sure our semiconductors are very stable, reliable, low leakage current. So now this is a table you can look at. This is all the high temperature electronics application. So but you have to build out your mind that the difference between the consumer electronics like our cell phone, our laptop is typical. We consider that this is running. This device will be used in the normal environment that a human can survive. So normally we test for this consumer electronics up to 75, up to 125. But there's several applications that we need that our devices are very robust. Like for example, automotive. So automotive in the automotive car here, we need to make sure that every component are very stable at a high temperature. There's several applications. So, for example, the one of most close to our life is this electrical vehicle. So inside this electrical vehicle, the peak temperature can be up to 150 Celsius degree. So therefore, we need to have the wide-bandgap semiconductor. But now you can see this is a prediction coming 2002. This is all the paper coming from the 2002. It's not the paper just coming from the last year. This is a 20 years ago literature. So 20 years ago, from all these experimental result, and then the very rigorous equation, we already make a prediction that the wide-bandgap semiconductor will be the important for the vehicle. So that also suggests that when we read the literature, actually the literature is very important. When you try to study the paper, when you try to look at all the recent 5 year or even the paper you publish, you work on or you will publish soon, it can be the truth for next 10 years, 20 years. For sure that many in the general community will always a little bit make the negative comments about the academic paper. We always talk about this just a pure like a paperwork. There's no practical value. This might be true for the other domain, but another domain in the semiconductor. In the semiconductor domain, every literature, every academic work can be the future for our technology, can be the future technology to sustain for the next application. This is one example. 20 years ago, literature already say that the automotive we need a wide bandgap, but nowadays it's pretty common sense that the silicon carbide gallium nitride already in our life. That's one of the example. Is the Tesla. If you look at the Tesla electrical vehicle car, not only a Tesla, nowadays many electrical vehicle car, they already have a silicon carbide base inverter. So this is also one of the interesting like the experience that you should think about. Don't underestimate the literature that you read it. Sometimes I know I can fully understand for graduate student, it's everyone will feel very annoying to study the literature, to read the literature, because you might feel like this is just too far from the practical, but it is not true, because it's indeed very practical. It's something that is going to be happen soon. So this is one example, and then for sure there's some other application that will need a very high temperature, like the turbine engine, like the space craft. So in the case of space, for the lots of the space exploration, we need to make sure that our semiconductor can sustain in the very extremely high temperature, more than 500, more than 600. So this is an example of a 550 Celsius degree. So the semiconductor need to be stable at that temperature. And then this is a domain that the wide bandgap semiconductor needed. So this is something just try to bring your mind that although this intrinsic carrier concentration, it looks like just a very simple, sometimes we easily ignore this equation because so far we just in the chapter 5, we haven't talked about the semiconductor, but this equation already good enough to tell us something more than this equation itself. It tells us some of the future that can address our the challenges here. So this is a 2002 literature. So let's just look at this is one example that I want to show that this continues. Every semiconductor technology requires 10 years, 20 years efforts, and the needs everyone's continue to work on from our past seniors until the young talents like you guys. So you can see this is in the NASA, there's one dedicated group work on the silicon carbide research, and for sure that from the last slide, you can fully understand this is technology needed for the space application. And then if you look at this is a literature in the 2017. It's not that new because now it's 2026. It's already 9 years ago. But 9 years ago already demonstrate the silicon carbide digital integrated circuit above the 800 Celsius degree. And this paper is published in the IEEE electron device, which is the most important journal for the semiconductor research community. If you got a one EDL, you almost graduate for your PhD. If you got a two EDL, you got your PhD. Not everyone in the PhD they have the two EDL. So anyhow, this is a very top tier journal. So you can see that from 2002, there's already the future forecast that the wide-bandgap, and 2017, this is experimental demonstrate. And if you look at the recent 5 years, 3 years, just put a silicon carbide space, you will still find out many research is ongoing. And this is something that from the fundamental academic put in the real application, in the end create a benefit for the future human society. So because this paper is all written in the native American, because NASA is another institute that easily to join, that unless for sure that you need to be qualified as a very higher degree, you need to have a very high level, but you also need to be qualified as an American citizen. So this is only the institute that the American citizens can work on. So it's worth to read that all this literature just published, written by the Native American. If you look at the course, there's no like Asia, there's all the Americans. So if you look at the paper writing, you found out that what they write here is also very simple. As I already mentioned in the introduction, that when we try to write the paper, it's not try to complicate everyone. We just want to make the story simple, convince, and everyone can understand. We're not write the paper like the novel that you need to read days and night, 1 month, in the end finally understand who is a killer, who is the actor. No, in the academic writing, we try to write it in a very simple way. Just try to be straightforward in the beginning. So if you look at the structure for this paper, this is a very nice structure and then very easily understood. So the first sentence here is a general overview. So wide-bandgap semiconductor theoretically enable 100 degrees Celsius degree increase in the semiconductor integrated circuit operating in the temperature over silicon and developed silicon carbide 3,5 nitride has been reported. So you can see the first sentence just a general overview. So every academic writing, the first sentence is just a general overview that the wide-bandgap semiconductor basic advantage and then what has been done in the past. So then the second will be the recent progress. So once finished a general overview, we'll start to move on a little bit overview and remind that what has been done recently. So there's a keyword, the recently, which is very often we use. So recently, silicon carbide JFET with a 2 level of interconnect have been studied to consistently demonstrate with 1,000 hours at the 500 Celsius degree, which is a significant step towards a new application, including the jet engine, ground test, Venus surface exploration. So far, still just like the writer story. So in the first paragraph, there's nothing that very difficult related to the technical academic equation. No, there's nothing related to academic, just a very general background overview and then just remind what we have been done in the past several years. Now we will start to move on a little bit more technical issues that we want to address. So normally we will have mention the issues, and then the first issue is general issues, and then the second one is more specific issues. So once we mention the issue, it means like something we try to attack to the recent like a society that there are so many, there are still like 2 issues that remaining in the academic world. That's why these 2 issues will become the motivation of this work. So once we understand the issue, we will start to mention the motivation. So like say, this is a quick go through this. The ability of operation stress semiconductor device at high temperature higher than intended has been proven to reliably assessment and qualification. Expansion of IC operation not presently envisioned yet. So that's the issue so far. And then this sentence you can see we previous report short-term silicon carbide JFET 700 amperes at temperature. So this is just they recall what they have been done. And then this is an attack to point out the issue from the previous work. And finally, the sentence here in the last sentence, just a key sentence, like try to summarize what has been done in this work. So he just used one sentence. It's good because of that means that the conclusion, if you can write the conclusion in the 1 or 2 sentences, that means that you can simply express what you want to say, and the reader can be easily understand. So if you ignore the whole part of introduction, just read the last sentence. The last sentence tells us that here we report operation test of similar silicon carbide JFET IC at ambient temperature up to the 961 Celsius degrees. So if you just didn't read anything for this paper, just read this sentence, you just already get in mind that this paper just talk about the JFET, silicon carbide JFET operation at least 900 Celsius degrees. That's all. So it's not that difficult, right? So this is very easy. If you look at the structure for their writing, it's very straightforward. There's no the very complicated discussion, and the conclusion is also very simple. He just used one sentence to conclude what they have done. So this is something that you should keep in mind, that when you try to write your own academic work, always try to keep it simple. I believe nowadays it should be much easier for everyone. You can write your own words and put it in the GPT, put it in Gemini. They can try to polish, but sometimes they will polish become way too good. So you just need to revise, because sometimes they will use the wording that just express way too good. For example, the excellent, outstanding. This wording sometimes has to be a little bit careful, because sometimes if your work is not that good enough, you claim your work as excellent, outstanding, you will be easily being rejected. You have to be more conservative. Okay, so now back to the fundamental part. So we have been already shown that the intrinsic Fermi level, and then also the concentration, and then this is a case that the electron and hole concentration are equal. So therefore we just put these 2 equations where NC exponential minus EC minus EFI over KT this is Ni. If Ni is equal to Np, where is Nv exponential EFI minus EV over KT minus. So that's electron and hole, intrinsic electron concentration and intrinsic hole concentration. So from this equation, we can start to estimate the EFI, which is equal to half EC plus EV and plus this additional term. and also can be rewritten if you express NV and NC. So you got this one. So therefore, you can find out that actually the EFI is not exactly in the middle between the conduction band and valence band. There's a slightly difference here, as shown me here. There's a difference between the EFI minus E middle gap. So now if you consider EC, EV, and then you define as a mid gap, which is EC plus EV over 2. That's we define as a mid gap energy here, which will be exactly in the middle. Therefore, you will find out that actually the intrinsic Fermi energy is not completely aligned with mid gap. There's a slightly difference. This is our EFI. So this is just some additional minus concept. Okay, so we will take breaks here, and we'll come back in the 15 minutes later. You can submit your homework and put your homework here.哦，那你把它印出来，对，然后你再写信跟我讲，然后再跟他，然后再跟你，不然等一下助教应该会来，你等一下再跟他讲，对。
怎么出席？
不会。
这个风波有办法补交吗？还是过期现在就可以？
你今天一定要讲。
啊，今天要
对，今天要讲。
哦，因为我忘记把它印出来。
OK，那你要等下中午会助教来，你要跟助教讲，你就今天交给助教。
哦，
对，然后我们2个人会来。
可能下午再去那个实验室讲。
对。
好，
那这些也是视觉。今天吗？今天吗？10月，我记得是说3月。
哦，是吗？今天可以啊，所以今天是一起，
就是用那个
Teams 嘛。
对，
好，
就是同一个时间。
可以啊，那就是一样4点半。
好，
那所以是哪一天？是
这个，这个只是为了把那个加进去。
OK，好。那这样的话，那你顺便就一样请那个现场跟那个学弟。
好。学弟的那个学妹，要跟新阳拿什么？
咸阳可能会在线。
他在讲，就是他比。
对，那你对。但是你可能还是让他知道一下。那可能你下次把那个会议的开头，因为这样的话我们有这两个。会议。好。比如说可能王子
那因为我常常用同一个那个。
就是同一个吗？
对，是同一个。
是同一个。
因为同一个时段，所以我就可以来。
那这样我会不会？那这样我是哪一个？因为这个都是2个都是 Microsoft 的。
没错，
是应该这个，这是 Teams。我觉得是这个，应该是这个。
还是我猜到点？
好像是，好像这个是 Teams。所以那个，对，这个是 Teams。所以应该是这个比较不错。这个只是我把它时间抓住。对，那应该是这个。
对，因为公司是不能设4点45的。
好。 Okay, so from the previous lecture, we have been many talk about the intrinsic semiconductor, but now we will try to add some more in addition to the intrinsic, because in the end we will not always use a semiconductor material that has exactly the same as N and P concentration. For sure, in the end, we will use N-type semiconductor or P-type semiconductor for the different kinds of application. So, the intrinsic semiconductor might be an interesting material, but the real power of a semiconductor is realized by adding small control amount of the specific dopants or impurity or oton. So we're adding the additional oton, and we will try to use this adding oton, try to a little bit manipulate the material's property. And this is something we call the dope semiconductor, and that's an extrinsic material. So in the case with a typical case with all the silicon otons in these regular lattice, is this something that we call as intrinsic. But now there could be the chance that we try to replace one oton with another different kind of species, and that we consider as extrinsic. So for example, we have a silicon otons everywhere, and then with a silicon oton, as you know that each silicon oton will contribute one. There's a 4 electrons in the outer shell, so each silicon will contribute 1. But now, if we consider adding a group 5 element, so we try to add a group 5 element here, which is arsenic, for example. So if we have arsenic, and therefore you will have 5 electrons. This is group 5, so that means you have 5 electrons in the outer shell. So you have 1, 2, 3, 4. But now there's 1 additional electrons here. So group 5 element has 5 valence electron. So 4 of these will contribute to the covalent bonds with the silicon oton, leaving the 5th more loosely bound to the phosphorus oton. So this is case with phosphorus, but we can also use arsenic. So this is a case where we consider as extrinsic. So because we have 1 additional of the electrons not bonding, so this electron becomes a free electron moving inside our semiconductor material. That will cause this material that has more electrons than the holes. So in the end, this will become as an N-type semiconductor material. So similarly, we can not only consider the N-type, but that could be have the P-type. So adding control amount of doping otons, either donors or acceptor, that can create the materials that we call the extrinsic semiconductor. So like what I have been drawn, this is a case with once we're adding as arsenic here. So as I say, arsenic have 5 electrons, 1, 2, 3, 4, and you have 1 free electrons moving. So this can be considered as an N-type. And one additional name that we consider that once we add the arsenic. So the arsenic has a 5 electron. So that means that this arsenic will kind of like the donate additional electron. So the donate, once you have the donate the additional electron, so we call this kind of the species as a donor. Because this is a additional species that can donate additional electrons, so that's what we call as a donor. And of course, once we have a donor, then we for sure have another opposite situation that we call as a acceptor. So let's consider again with a silicon lattice. So as the same, we have a but now if we consider that we add as a boron inside this material, the boron only have 3 electrons in the outer shell. So which means we have a 1, 2, 3. Only 3. Only. That means the bonding between this boron and silicon, there's a 1 empty place. This is 1 empty. There's no any electrons will be bonding because the boron has only 3 electrons in the outer shell. So therefore, this we don't call it empty. We just call it as a hole. And this hole is a place that another electron can be moved in. And because of this hole can accept electron, so therefore we call this as an acceptor. So the concept of donor acceptor is not that complicated. Just one the case you have 5 electrons, so that's why you donate one to another. That's why we consider as a donor. And then for the acceptor, it's just the boron has 3 electrons, so there's an empty place, and therefore you can accept 1 additional electron from somewhere else, and that's we call this as an acceptor. So an extrinsic semiconductor will have either of full of the electrons, that would be N-type, or a case with a full of the holes, that will be considered as a P-type. So in this case, this will be the P-type. So basically, we just try to add the group 5 or group 3 material, then in the end we can change the material property for either that has a larger electron, which is an N-type, or either has a larger P-type holes. Either has a lot of holes. That's for the P-type. That's what we call the P-type semiconductor. To further understand this kind of the additional species added inside this semiconductor, we can also consider as a concept of band diagram. So first, let's consider as a donor. In the case we're adding there's a donor atom, because a donor is this adding atom is coming outside from the original lattice. So sometimes we also consider this is impurity, because this is not the original layer. This is some coming from the outside of their system, so we consider as a impurity. So therefore, we consider that in general as a donor impurity atom, like the arsenic in the previous case. And also we can use the concept of the energy to understand the impact of the donor impurity atom. So we call this as a ED, the donor energy here. So the donor electrons can be elevated into conduction band. Leaving behind the positive charge. And the electron in the conduction band can now move through the crystal, generating a current, while the positive charge ions is fixed in the crystal. So this will cause a material that we consider as a N-type material. So this text, to be honest, is not that easily understood. So it's better just use a band diagram to understand. So therefore we have the EC, EV here. We have an EC, EV here. Because we add there's a donor, so we need to consider as a separate energy called ED. So ED here. And then this donor electron can be elevated to the conduction band. So that means this donor electron can be jumped to the conduction band, and that will leave as a positive fixed charge here. And this electron in the conduction band will become, that can be moved inside the crystal, in the end become as a current. So this is exactly that how this text try to explain, just can be simply understand from here. And the approximate energy required to elevate the donor electron into the conduction band, this is an energy that this electron need to overcome and jump to the conduction band. And this energy is referred to as ionization energy. Which is here. The distance between the conduction band and then the donor energies that we call the ionization energy. So from this schematic, we can also easily can imagine if ED is getting close to the EC, for sure that you will have more electron easily to jump. If the ED is far away from EC, you will have a difficulty that electron, this donor can provide the electron, jump to the conduction band, become the current. So the ionization energy, this kind of concept become very critical, because of if the ionization energy is smaller, then the donor can easily contribute the electron, become the current. If the ionization energy is larger, then the donor doesn't try to contribute the electron, because it's difficult to jump from the ED to the EC. So therefore, we can also interpret the concept of ionization energy as if we have the ionization that is small. So this distance is getting small. That means that the lots of electrons can easily jump to the conduction band. Therefore, electrons in the conduction bands are increased. Right, so this concept is similar to the one we have for the Fermi energy, but now we just use the concept of ED, because the ED close to the conduction band, you have more electrons, and then ED is far away from your conduction band, you have a less electron. So similarly, we can also apply this concept for the acceptor as well. So in the sense of acceptor, we just define as a acceptor energy level EA here. And still the same, this electron position can be thought of as a holes. This empty electron position can be considered as a holes in the semiconductor material. Then the hole can move from the crystal and generating a current. While the negative charge boron atom is fixed, and this can be considered as a p-type material. So this text also still not that easy to understand, but we just use a Venn diagram for us to understand. So we have EC, EV, ECEV, but now we have the acceptor energy level here, EA, acceptor energy level. So similarly, the concept is that we can have the holes contribute here. And then we will have the negative charge, fixed charge left behind. And then the distance between this EA versus EV is the same. We call as a ionization energy. So now, once we have the concept of ionization energy, we can look at several practical cases that we have the silicon, germanium, we have a different donor, we have phosphorus, we have arsenic. For the acceptor, we have a boron, we have aluminum, and you can in general see that these ionization energy are very small. So, for example, in the case of silicon, this ionization energy is smaller than 0.1 electron volt. So, ideally, if you try to look at the EC versus EV, and in the case with the silicon, let's just put as a acceptor as a one example. We have the EA here. And that has energy 0.045 electron volt, like in the case of the boron here. And this one is extremely small. ionization energy. So that means if you try to dope the boron with a concentration of 10 to 20, because of the ionization energy is very small, so therefore you can expect it that more than 99% of the boron can contribute the whole. So therefore, you will roughly get the whole concentration similar to your dope boron concentration. This is for silicon is not the issue. So most of us will ignore, because in silicon case the ionization energy is very small. So therefore, whatever you dope for the boron, for the aluminum, for the phosphorus, for the arsenic, so we dope 10 to 20, and then we got the electron concentration 10 to 20. We dope the acceptor 10 to 20, we got the whole concentration of 10 to 20, because the ionization energy is very small. So in the silicon world, most of people will just forget it. They understand this when they study the semiconductor physics, but in reality, just the ionization energy is way too small. So lots of people forget that the importance of the ionization energy, because in silicon it's just way too small. But however, in the other material, we will always suffer this ionization energy, because of in the other semiconductor material, the ionization energy is not that small. For example, in the case, especially in the very exotic material like the wide-bandgap, like the 2D, like whatever, this very fancy material, they always suffering that has a large ionization energy. For example, in the case with the gallium nitride, so this is a conduction band, this is a valence band. If you try to dope the gallium nitride with a p-type, you still need to consider the acceptor energy level. Roughly around here. But the challenge is that this ionization energy level is not that small. This ionization energy can be larger than 0.3 electron volt. Just a case that the different material, different doping has a different number. In anyhow, that is larger than the silicon. Silicon is always like less than 0.1, but now we have more than 0.3 in the case of gallium nitride. So if you have a larger distance here, so that means you actually have less effective holes can be jumped to the valence band and become the conducting holes. So normally it's less than 10%. Ionize. For silicon, doping N-type, P-type is never as an issue, but for other material, try to make the good doping for the N-type, P-type. In the gallium nitride, in silicon carbide, in the 2D, in the other material, in the gallium arsenide, it's always very challenging because of the ionization energy is very large. So that will cause, in this case, if we have more than 0.3 electron volt, we get less than 10% ionized. So what does this mean? This means in the gallium nitride, we normally dope the magnesium as an acceptor. If you want to dope the magnesium for the doping concentration, like say 10 to 19, but you only have a less than 10% ionized. So in the end, you have less than 10 to 18 hole concentration. So that's become the issue. So you are not easy to make the N-type, P-type in the material, not that simply like the silicon. You have a very difficult to make the P-type in the gallium nitride, in the 2D material, in the silicon carbide, in the many different material. As the material is getting more fancy, it's getting more difficult to make the very good N-type or P-type junction because of the ionization energies become larger than the silicon. So this is the challenge that we will face in the real world, but the fundamental concept just this ionization energies is larger, and because of silicon we almost ignore this issue, but in the other material this issue is very very challenging. Okay, so now we're back to this electron and hole concentration. So let's still do the state by state to look at how this Fermi energy. In the previous slide, we talked about intrinsic, so your EF is roughly in the middle of between the EC and EV. So you get the N0 is equal to the P0. But how we can also use the same concept applied to the different Fermi level position. So still the same, we have this conduction band, valence band. So we have a EC, EV. But now our Fermi energy is close to the conduction band. So then what would be the electron hole concentration look like? Of course, the previous equation already told us that we have the higher electron hole concentration, but how can we also understand by using this distribution? So again, we plot the GC and GV here. We have a GC and GV, but now our EF is close to our conduction band. So that means our whole distribution will be moving upper. So then you will see the whole distribution will be moving upper. So therefore, this will cause, I should try to redraw again. So therefore, the overlap region for this EC versus GC will become larger because of you try to move this figure, this distribution towards the up, and therefore the overlap region will become larger. So once the overlap region becomes larger, so this suggests we will have a larger density here. With a larger electron density and then a smaller hole density. So that's why this material we can consider as an N-type material. So this is the same conclusion that we already get before, but now we can use another way to understand. So the same drawing is shown me here. As long as we have this FFE original is here, but once we have a Fermi energy moving upward, so you will get this FFE shift upwards, and then therefore your overlap region will become larger. So this area will become larger. So therefore the conclusion, and this will become smaller. So the conclusion is, if EC minus EF decrease, then we will see the N0 increase. But on the other hand, if EF minus EV decrease, that also suggests that we will have a P0 is increased. So it's either your Fermi energy close to your conduction band, that means that you have more electrons than holes. Your Fermi energy close to your valence band, that means you have more holes than the electrons. So furthermore, we can still play a little bit about the equation where we have before. So now we have a very general thermal equilibrium electron concentration where N0 is equal to NC exponential minus. Now we consider try to have the certain additional EFI, but in any way will become EC minus EFI plus EF minus EFI over KT. And this can be further derived as NC exponential minus EC minus EFI over KT exponential EF minus EFI over KT. And then the first term is intrinsic carrier concentration, where we have derived before. So where we have been shown the Ni is equal to EC minus EFI here. So this just play a little bit between the N0 that we have been shown, but now we try to incorporate the concept of the intrinsic carrier concentration. So with all this equation, we can start further play a little bit more about this equation. So for this calculation, it's nothing special, just a little bit calm down, take your time. You will figure out how this equation is coming out. It's just play with a new parameter and replace it with Fermi energy and so on, so on. You will get this. So therefore, we can still consider our N0 is equal to Ni exponential EF minus EFI over KT, and P0 as a PI exponential minus EF minus EFI over KT. And therefore we just put this N0 times P0, which is equal to NCNV exponential minus EG over 2KT which is also equal to Ni squared. So in the end, we got this what we call the mass action law. Intrinsic carrier concentration of N0 times P0, that will be equal to as a Ni squared. So that's in the end the new equation we can get it. The calculation here that I will prefer not to spend too much time to derive. You can quickly go through it. I think as you guys that have been learned from the junior high, senior high, undergraduate, all your life so far is trying to calculate, solve equation. That's how the most of our local Taiwan students from my past learning experience that we have been teach how to solve equations since elementary, since junior high, since senior high, since undergraduate. So for these courses, I will less prefer to continue to teach how to solve this equation. This all equation just you can easily get it. I believe with everyone's knowledge, you are able to solve it. But also, if you look at the textbook, you definitely can understand. So this should be not the focus on this class, that we still do the step by step to derive equation for everyone, because this will become just similar like the textbook teaching. Then you just read the textbook. Why you have to come to the class? You have to come to class because you have to learn something that the textbook didn't teach. Where I feel the physics-based understanding and all more relevant for the real world issue, the real semiconductor device that you will face, and how to apply this knowledge, how to interpret this knowledge to connect to the practical case is getting more important, because this is something that the semiconductor textbook will not teach you. This is all the experience I have learned from my undergraduate who learned the semiconductor till so far. I feel like the certain part that's useful is beyond their equation rather than just pure calculation. For sure, the calculation is still important because you need this for homework. You need this for the exam to have the fair evaluation for everyone's grading. We still need to ask everyone to do the lots of calculation for the homework exam, because that's a more fair evaluation. If I ask you, the question is more like the open discussion. It's very difficult for us to do the grading. Okay, so since we talk about the extrinsic semiconductor, there's one additional concept that we call the degenerate semiconductor. The idea is also not that difficult. If you look at the textbook, sometimes might be a little bit confused, especially if you try to read the Mandarin one. that's very confused because their translation, as far as I know, they call this as a 简并. I cannot understand why they translate this. But the concept here is just very simple. As we already say, we have in the semiconductor material, we have this conduction band, valence band. And then we all know that when we try to dope the semiconductor, we can start to manipulate your Fermi energy. If you dope concentration higher and higher, then you're moving close to the Fermi conduction band. If you dope the p-type concentration higher, your EF will moving close to a valence band. But in reality, there could be the one case. You just dope too higher than that your EF is beyond your conduction band. So that's what we call the degenerate. So therefore, the degenerate semiconductor is a case that your EF, you just doping too high, you just dope too much, way beyond, then your Fermi energy is moving above your conduction band. This is how we call the degenerative dope N-type. So this is when the concentration of electron in the conduction band exceeds the density of state of NC. The Fermi energy lies within the conduction band. This type of semiconductor is called the degenerate N-type semiconductor. So in other words, just you dope too much, so therefore your EF just beyond your EC. So similarly, you can also have the degenerative dope p-type. So the concept is still the same. EC, EV. But now, because of your concentration of holes exceeds the density of NV here, which means now you have an EF below your valence band. And this is a condition we call as a degenerate p-type semiconductor. So that's also possibly happen. Okay, so let's consider some of these the donor concentration in the band diagram where we have been already mentioned. Once you have this donor atom, we'll consider this donor energy here, and we also consider the ND is the concentration of the donors atoms here. And therefore we can consider that, assume you have 10 electrons. So you have a 10 electron, which is your ND here. And then now you have the 9 electrons will be able to move in. You have this one will be jump into your conduction band. So therefore you have a 9 electrons here. And then you have a 1 electron in the left in the donor state. And also because you have 9 electrons moving in the conduction band, so that's left a 9 positive charge. You have a 9 positive charges left. and here we call the ND plus. And then 1 electron in the donor state we call the ND. And in the beginning you have a total 10 electrons. So that's we call the ND. And the reason why I have to use this number is I want to explain why this equation makes sense, because this equation just tells us, if you just look at this, the definition sometimes get confused, but you put number, you get more easily understand. So you have a total 10 electrons in the donor state, and 1 is moving, 1 is left in the donor state, and 9 is a 1 that your electron jump, and then there will be a 9 positive left. So this will still remain as a true, where this plus this one is equal to this one. So that's the main purpose to explain that in this line. So in the end, we can able to have the equation to understand that how many electrons in the donor energy state, and then how many positive charge donor states. That's what we also call the ionized donors. So therefore, your ND can be rewritten as here. This ND is a concentration of electron in the donor energy state. So this is here. And you have ND plus is a concentration of a positive charge donor state. That's ionized. Can be also calculated here. So one of the confusing that easily come from to understand the semiconductor physics and device, because they have a lot of abbreviation term that are very similar, and then this is something that you need to take time to understand. Okay, so because in the previous we have been mentioned that these statistics, and then therefore we also want to apply these statistics for this donor and acceptor. Still the same, we will use a probability function likely shown me here, but there's a slightly difference from the Fermi-Dirac functions here, but we won't talk the details. If you are interested in why this equation look like, I believe you are able to find more information in the textbook or online. So now we consider the ND, where we have been shown before is a concentration of an electron in the donor energy state. So the ND can be expressed as shown me here, and then 1/2 factor is written as 1/G, because G is called as a degenerative factors, and PA is a concentration of hole in the acceptor energy state, and where PA can be also calculated as shown me here. And with this concept, we start to do some approximation where we'll consider our ED minus EF is much larger than KD. With several iterations, finally you will reach this equation, where your ND is your electron in the donor state over your ND plus N0, which is correlated with EC minus ED. And EC minus ED just the ionization energy of a donor electron. So this term is ionization energy. I know this is a calculation, this equation is confused. So let's just look at some of the numbers that will help you to get some more sense. So if you consider that you want to determine the fraction of the total electrons still exist in the donor state, at the 300K. So we can try to use this equation, which consider as this one. This is ionization energy. So now you can see this only 0.41% still left in the donor state. So that means we consider this ionization energy in the silicon only 0.4% electrons still existed in ED. So that means you have more than 99% electrons in the conduction band. That's why we call this a case almost like the completely ionization. So that's why in the case with the silicon, is almost nobody really care about this ionization issue, because as you see here that you dope, but it's more than 99% the electron. You can this donor state, this donor can contribute more than 99% electron in the conduction band. It's considered as a complete ionization. So this example shows that there are very few electrons still in the donor state compared to the conduction band, and this can be considered as a complete ionized here. So that's the case with silicon. But if you try to think about, you place this number as a 0.3 electron volt, then you will see the huge difference. If there's another donor state energy has an ionization 0.3 electron volt, then you will see the huge difference for this. You will see that there's quite amount of the electrons still exist in the donor state rather jump to the conduction band. So continue, we will start to try to consider this ionized donor, and then to calculate consider the whole system as the charge neutrality. So this charge neutrality condition is used to determine the thermal equilibrium electron hole concentration as a function of impurity doping concentration. And first of all, before we move in for the equation, we have to get this a whole picture where we consider this as a compensated semiconductor. This is like a whole picture that you consider part of a charge is being ionized, part of it is non-ionized, donors and acceptor. So still the same, we have the conduction band and valence band. We have conduction band and valence band, but now because we consider the full picture, so we should both consider the donor state and acceptor state at the same time. So we have the donor state ED, we have the acceptor state EA. And we have some part of the donors that are being able to ionize. So we have some of the donors is able to ionize, become the electrons in the conduction band. So this is where we have here. But this one will left a certain negative charge here. And then we'll also have some part of the acceptor is being ionized. So this is ionized donor. And also the ionized acceptor. But we still have some part of that's non-ionized. Show me here. It don't contribute any. So that's an unionized region. And also for the semiconductor that we also have to take into account, there's a thermal generated electrons. Right, this is due to the thermal. So that's a thermal related electron holes here. So therefore, we can start to apply the charge neutrality, which our N0 plus the Na minus is equal to the P0 plus Nd plus here, where the N0 and then the P0 is a thermal equilibrium concentration, and then the NdPa is a concentration for the donor energy state and acceptor energy state. And also, we consider the ionized donor, the concentration of a positive charge, which is ionized donor. Here can be considered. This is something that we have also shown before. This is Nd plus is equal to Nd minus the capital Nd minus Nd here. And then the Na plus here, Na minus is the capital Na minus Pa here. This is ionized acceptor. So in the end, you put these two in here and here. So you got this general form for the charge neutrality, where N0 plus Na minus Pa is equal to P0 plus Nd capital Nd minus Nd. You need to spend a time think about this, because the challenge for this understanding is not the mathematics. It's just this denotation, this term just looks very similar. They just have a capital small word with a positive and negative sign. But just think about this. Just all the positive charge is equal to all the negative charge. So in the end, you get this charge neutrality equation. So finally, with this is a general form. This is a general form here. But if we consider as a special case as a completely ionized, so completely ionized, that means that the carrier density in the donor state and then the acceptor state are both zero. So therefore, you can simplify the previous one equation and lead to this simplified equation. And furthermore, we put this N0 P0 equal to Ni squared. That's a mass action law. So then you can get this one, and this one is become this equation. That's very easily to solve. So in the end, you can have N0. Which is equal to Nd minus Na over 2 plus Nd minus Na over 2 which is this one. Thus we can finally have the one equation to derive for the N0, the thermal equilibrium electron concentration, and also we can have this P0. So finally, we have this general form that be able to calculate the thermal equilibrium electron and hole concentration. And then this equation is actually very useful because as long as we know the p doping, and then this is also considered as the compensate material. So what does mean the compensate? Compensate material, means that this is material that could be both have the p-type and n-type together. And in reality, we always has a material that probably has a material that in the beginning as a p-type, but afterward we implant it as an n-type. So we are curious that what would be in the end, what would be the net electron concentration? For example, like the case here in the MOSFET. So if you are a little bit familiar with semiconductor process, we always starting from the piece of a material which is, for example, p-type substrate material, and then we'll do the implantation. We do the implantation in this source and drain region. Which we will implant as a n-type, and then with reach to the n plus, and in the end we do the oxidation, we do the gate. So from this process, you can start to, you should be aware of that in the source and drain region, this is the source and drain region. This is a region not actually coming from the one kind of the carrier. It's starting from p-type and then implant with n-type. So this is a region where we consider as a compensate semiconductor. That means you both have the two kinds of carrier that both existed. So to further have the accurate way to estimate the concentration in this region, that's why we need to have this equation, because in this region you will have the n plus, which is nd n-type of doping. You have a n plus doping, right? But also in this region you have a background substrate doping, which is Na. That's a p substrate doping. So with these two information, finally you are able to estimate the net electron concentration in here. So that's why we spend the time to derive this equation. This is a case that in reality we will really face, because you will have the p-type material, you dope the n-type, and then you will be interested to know what would be the electron concentration in the net, which we can use this equation to calculate for the estimation. Okay, I think I probably will stop here. It's just a few slides more, but we will stop here. We'll continue on the next time. And by the way, just mention that on this Wednesday at 6 p.m. we will have the mega class because I was absent from last Monday. So this will be the same classroom here. And then if you will be able, you will be available. You are welcome to join this mega class. Okay, so see you.